In this second of a two-part series, let's explore cumulative distribution functions, or CDFs, for discrete random variables. Suppose we get to randomly sample a number x from 1, 2, and 3. Since we select a number at random, x has a discrete uniform model. That is, x has an equal 1/3 probability of being either 1 or 2 or 3. Consider the CDF of x, f of t, the probability that our selected number is at most t. As with a continuous CDF, though a discrete model is only defined at a discrete set of points, its CDF is defined across the entire real line. Let's start it by exploring the CDF at values t that are below the support of our model. For example, what's the probability that your randomly selected number is 0 or under? Well, the smallest number that we can get is 1, so there's a 0% chance that our number is at or below 0. That is, the CDF at 0 is 0. In fact, for any t below 1, we haven't yet accumulated any mass. Thus, the CDF for t values in this range is always 0. Moving along the real line, the first place that we can accumulate any mass is at 1. So what's the probability that your number is 1 or under? This can only happen when x equals 1, which has a probability of 1/3. Notice then that at t equals 1, we accumulate a mass of 1/3. Thus, the CDF makes a jump up from 0 to 1/3. Moving along the real line, consider what happens between the numbers 1 and 2. For example, what's the probability that your randomly selected number is 1.5 or under? This can only happen when x equals 1, which has a probability of 1/3. And this is true for any t value between 1 and 2. We don't accumulate any more mass in this range. Thus, the CDF has to remain flat at 1/3. Moving along further, the next point that we can accumulate any mass at is when we get to 2. We can get a value of 2 or under in two ways, when x equals 1 or x equals 2. These two events have a total probability of 2/3. Thus, at t equals 2, we accumulate another mass of 1/3, and the CDF makes a jump up from 1/3 to 2/3. Moving along, consider what happens between the numbers 2 and 3. For example, what's the probability that your randomly selected number is 2.5 or under? This can still only happen when x equals 2 or 1, and this has a total probability of 2/3. Thus, just as was true for t values between 1 and 2, we don't accumulate any new mass between 2 and 3. Thus, the CDF remains flat at a height of 2/3. Now we're almost done. The next point where we can accumulate any mass is when we get to 3. We can get a value of 3 or under if x equals 1 or 2 or 3, which happens with a total probability of 1. Mainly, your number has to be a 3 or under. Thus, at t equals 3, we accumulate our final mass of 1/3, and the CDF jumps from 2/3 to a height of 1. And then it stays there. For example, our number has to be a 4 or under, with a probability 1. Mainly, for any t above 3, we've already accumulated all of the mass from the model. Thus, this CDF stays flat at a height of 1. Stepping back, we started with a discrete uniform PDF on the values 1, 2, and 3. We then built a corresponding CDF with 4 cases or pieces. When t is below 1, when t is greater than or equal to 1 but less than 2, when t is greater than or equal to 2 but less than 3, and when t is greater than or equal to 3. Though the CDFs will look different for other discrete models, they share similar features. First, a CDF starts at 0, either exactly or in a limit. The CDF then makes a jump at each possible outcome of the random variable x, where we accumulate mass. The height of the jumps at any given outcome t is p of t, or the probability mass function at t. The fact that all of the jumps here have the same height reflects the uniform nature of the x values. That is, we accumulate a mass of 1/3 at each of our possible outcomes, 1, 2, and 3. In between the possible outcomes of x, we don't accumulate any mass, thus the CDF stays flat. Finally, once we get beyond the range of possible x values, we've accumulated all the mass there is to accumulate, thus the CDF stays flat at 1. In conclusion, the CDF for any discrete random variable x, big F of x of t, is defined as the probability that x is less than or equal to t. And since x is discrete, we can calculate this probability by summing up the PMF, P of x, across all x values that fall at or below t. Further, all discrete CDFs share some properties. First, just as is true for continuous CDFs, the output of a discrete CDF will always be between 0 and 1. After all, it's a probability. And a discrete CDF is non-decreasing. But unlike a continuous CDF, a discrete CDF is a discontinuous step function. Next, these step functions are always right continuous. And finally, a discrete CDF will always approach the limits of 0 as t goes to -infinity, and approach 1 as t goes to +infinity.